Okay, so let's take a look at the next one. It says, so hopefully these ones came through pretty quickly. Quick note, you probably could have figured out velocity by plugging it back into acceleration because you had the centripetal acceleration. You could have plugged it into v squared over r. That would have been just fine. You get the same answer. I just took the 2 pi r over t route, so no difference there. Just maybe quicker or using answers that you already had definite values for, which is a good trick to use. Otherwise, you're worried about error carried forward in case you messed up this value here. So, all right, looking at the next one, it says a plane is moving at 400 meters per second. So that's its velocity because it says meters per second. So we're looking at linear. So 400 meters per second. And it's making a circular turn with a radius of 3 kilometers. What is the centripetal acceleration? And then the next question is, what is that in terms of G's? So thinking about this in kind of airplane, Top Gun style scenarios, we'll take a look at that for just a second too, because that'll kind of help us get set up for gravitation. So this is a pretty straightforward question. Acceleration is equal to v squared over r. So we're going to plug that in. Don't get tripped up by the radius. It is 3 kilometers. That is 3,000 meters. So plugging in and solving, you get 53.3 meters per second squared. So that is the centripetal acceleration. In order to figure out what we get in G's, we're trying to figure out how many gravitational fields basically is that, or how many times the force of gravity is this person who's in this plane getting impacted by that. And so all we have to do to figure that out is just divide it by 9.8 because you treat it like a conversion. So 1 G is 9.8. So how many G's in 53.3? Because 9.8 again is an acceleration. So we're taking acceleration, dividing by acceleration, we're getting G's out. We should get somewhere around 5.4 G's. This goes to like, oh, what can a human withstand in terms of like turning in circles? If you guys think back to all those kind of funky tests that they used to run on pilots and that sort of thing, that's where that comes from. I think it's somewhere around 12 that most humans can withstand before they start blacking out and all that good stuff. So this one gets kind of interesting. So it says a 2 kilogram ball is attached to a 1 meter rope. Calculate the force of tension on the rope if the ball is moving at 20 meters per second and at 5. So we're going to kind of split our paper here. We're going to do the 20 meters per second first. So we have a mass of 2 kilograms. We have a radius of 1 meter. That's nice. Thank you. And a velocity of 20 meters per second. So taking a look at centripetal force, that plugs in really nicely. So force centripetal is going to be equal to mv squared over r. Again, mass times acceleration. Once we plug that in, we get mass of 2, velocity of 20 squared divided by r. And so in that case, we get 2 times 20 squared divided by 1. And we're going to get somewhere around 800 newtons. Now, this isn't the best possible answer. If you guys look at the very bottom, it says tensions at low and high speeds. We can consider 20 meters per second to be a high speed. We can consider 5 meters per second to be at a low speed. So if we look at this ball getting attached to the 1 meter rope and getting swirled around like a tether ball, if that's kind of the situation that we have going on, oh, I do not need this thing sliding on me right now. Come on. There we go. Stay. Okay. So if we look at that sliding around, sorry, I'm losing my lights here. So that's swirling around. And as you're doing that, that's not the only force acting on that ball. We have our friend gravity acting on that ball. So if we look, and now if we swing this around, it's going to be nearly horizontal because we're swinging it around really, really, really fast. But we have this tension on this rope. It's going to be sagging a little bit. So we have that full tension force, and we can bust that up again into our tension in the y direction And our tension in the X direction. Well, again, what's causing that tension in the Y? That's going to be mg. So mg is going to be pulling down on that ball as it's swinging around. So we really should be adding in that mass times acceleration due to gravity. Now let's see what happens with that if we do it at a high speed, like 20 meters per second. So how do we best figure this out? Well, if we want to figure out this tension force here, this is a Pythagorean theorem question, super easy squeezy. So we're going to take Pythagorean theorem, square root of tension in the X direction plus tension in the Y direction, oops, squared. And when we plug that in, we know that mg, so our tension in the Y direction is going to be 9.8, so that's going to be 9.8 squared. So we're going to take the square root of, or sorry, how many kilograms? 2 kilograms, my bad. So 2 mass times acceleration due to gravity. So 2 times 9.8. This here in this X direction is going to be equal to the tension on the actual string itself. So that's going to be the 800. So we get 800 squared times 2.98 squared. And we wind up, once we kind of cycle all that through our calculator, we get 800.24 newtons. Wah, wah. So if we look at this, we're like, okay, 800.24 versus 800. Well, something that's already 800 newtons, what's another 0.24 newtons? It doesn't really make that big of a difference. But let's take a look at what happens when we slow it down. So now if we're spinning that ball a little bit more slowly, gravity's going to start taking over a little bit. So we have to include that again. So if we have our mass as 2 kilograms, and our radius as 1, and our velocity as 5 meters per second, we're going to plug that in as Pythagorean theorem. So if we say just the centripetal force, we want to just look at centripetal force, we can do mv squared over r, and when we plug that in, we get 2 times 5 squared divided by 1, and we get a force of 50 newtons. Well, if we take that and we add to it, or we try to Pythagorean theorem to figure out what that angle is doing to that particular rope or doing to the tension on the rope, we're going to take the square root of 50 squared plus 19.6 squared, which is 2 times 9.8, right? That came from over here. So we have 50 squared, which is that tension that we calculated, or that centripetal force, and then, so that's going to be our X, and this is our Y. And once we do that and we calculate that out, look at that, we get to 53.7. So that's a difference. When we're comparing 50 to 53.7, I mean, that matters, right? 800 to 800.24, give it a rest, right? It doesn't really make that big of a difference. So when we are talking about tensions at high and low speeds, if you're at a lower speed, so at lower speeds, you've got to account for mg. And use the Pythagorean theorem to solve. At higher speeds, doesn't really make a difference. You're like, well, Misty, how high is high enough? You know, you ask great questions. I think it really kind of depends on how heavy your ball is. It also kind of depends on where, you know, you have to kind of look at this equation a little bit and see how are these numbers going to play out. Is this velocity squared going to really, really help out this mass compared to this radius? What's really going on? You can always err on the side of caution and just do it this way every single time. And if you have this little extra bit in here, you wind up sig-figging it out anyway. But you know, in this one, for this particular example, the difference between 20 and 5 was enough. So just remember that if you're looking at twirling ropes in a horizontal fashion, if you're doing it slowly, you need to account for gravity, because gravity is going to start kind of tugging down on that. It's going to change the angle. Once it changes that angle, it's going to change that tension. So just be mindful of that as you're working through problems like that.